Hi, and welcome to Live Here. In today's session, I'm going to talk about Transformer Chatbot First Pass. So I am calling this as a first pass. So we'll use the transformer in a chatbot scenario. So we'll ask a question and generate an answer for sure. But in this section, I'm going to use a very simple data. So not to complicate things, we will try to understand how the transformer works with a simple data, and in the next subsequent classes we will deal with the more complicated data and use a transformer for our chatbot purpose, or train a transformer for our chatbot purpose. So here, code a transformer model with simple data. So what are the steps that you'll be taking is word embedding, positional encoding, attention class, uh, encoder-decoder class, a transformer class, trainer transformer, and finally model inference, right? So word embedding we did discuss in a lecture a few weeks ago. Positional encoding is what I'm going to talk about now. We also have the attention class discussed in the last few lectures. Encoder-decoder class we'll discuss in this lecture. Define the transformer class and the rest too, right? Okay. So what is positional encoding? So the positional encoding is a technique that transformers use to keep track of word orders. We'll convert the phase pizza is awesome to positional encoding, but before that pizza is awesome end of sequence is converted to a word embedding. So word embedding, we are creating two word embedding values. So that means that each word can be defined with two values, right? But in actual scenarios, you'll have a word defined with hundreds or even thousands of word embedding values. So attention is all you need paper has it defined as 512. So each word is defined with 512 values. But anyway, because we are keeping this simple, we'll create a word embedding value for 2. Okay, so pizza is awesome, and this is word embedding values for each of the tokens over here, and that's the positional value. So let's discuss about the positional encoding values. Now we add a set of values that corresponds to word orders for a set of word embedding. The numbers that represents the word order comes from a sequence of alternating sine and cosine squiggles. So these are my word embedding again, and here we are now going to fill it up with sine and cosine squiggles or the positional encoding value. So there might be many different ways of doing this positional encoding, but attention is all you need paper talks about this technique, so we'll stick to this technique. So we had word embedding 1, word embedding 2, and then we have sine and a cosine graph. So those are 90 degree apart of each other, and the value is between -1 to 1, right? So each squiggles give a specific position value of each word embedding. For example, the y-axis value on the green squiggle gives positional encoding value for the first embedding of each word. Word 1, word embedding 1 has a y-axis value of 0. Word 1, word embedding 2. So because there are two embeddings, so one per word. So this is my word 1, which has what values 0 and 1. See, on the y-axis, which has a value of 1. Okay, so we get the positional values based on the y-axis. Because the sine and the cosine words are repetitive, it might be possible that two words might get the same positional value, y-axis value. The more embedding values we have, the wider the squiggles become. So what it means is here the frequency is it's very compressed, and then once it keep having more word embeddings, it gets spread it out. So it just spreads out, right? So that way you get different values, right? And you end up getting different values. So now after we have defined those positional encoding. So you have these values as positional encoding for the word for the sentence pizza is awesome, end of sequence. Okay. Okay, so now we add up these. So point 20, so that's my word embedding 1 for this word 1, word embedding 2 for this word 1, right? So these are the values that we end up with. So if the position of awesome and pizza is interchanged, then we have new values for positional encoding. This positional encoding allows transformers to keep track of words. Right. So pizza is awesome, awesome is pizza. So notice that we might have the same word embedding value, right? But when it goes into positional encoding, so because the values will differ, so at the end, when we get the final value, this will be different from what we have here. Pizza is awesome, right? Okay. So now let's discuss about the type of data we are using. So token to ID, what is live AI, awesome, start and end tokens. So we have 0, 1, 2, 3, 4, 5. These are my token values. And this I'm going to use it for my encoder input. So encoder input is a torch tensor. So notice everything has to go into a float. Okay. So we are not going to deal with integers. It will be floats. Anyway, token to ID, what is live AI? Live AI is what? So this is my question. Okay, so this is my question and the decoder has to answer it. So the decoder has an input and decoder has a target output. My target output is awesome end. Why end? Because end is so this in decoder has to predict the end of the token to give the right answer, right? But it also needs an input. So it has start, it begins with a start token and then followed by the all the non-generated tokens or the partially generated tokens. So awesome. So for example, start awesome is could be something we could have, but here I'm just using start awesome. Okay. So this is what you feed into a decoder at each time step during training. It starts with a start token followed by the partial or generated output so far. Awesome. So purpose allows the decoder to learn to generate the next token given prior token. So if I have a start and an awesome, it has to predict awesome and end. Okay, so now it's the we'll dive more into the rigorous topic of positional encoding. So notice here we have NN module that is taken from the PyTorch NN module library. D underscore model is the dimension of the transformer, which is also the number of embedding values per token. In this example, D model equals to 2. However, in attention is all you need D model equals to 512. So maximum length equals to maximum number of tokens we allow as input. So since we are pre-computing the positional encoding values and storing them in a lookup table, we can use D model and maximum length to determine the number of rows and columns in that lookup table. In this simple example, we are only using short phrases. So we are using a max size of 6. However, in any annotated transformers, they just usually set to a very high value around 5000. So max length is 5000. Okay, so now we are initializing the position encoding values with torch.0. So max length is 6 and D model is 2. So just to give you an idea what that does is 0, 0. So it just gives you a tensor value of 0, 0, 0, 0, right? So yeah, so that's how you are initializing it. So position equals to torch.arrange start 0 end max length step equals to 1 float and unsquared. So defining the positions here. So now we create a sequence of number for each position that a token can have in the input or output. For example, if the input token where I am happy today, then I would get the first position 0. Happy would get the second position 1 and today would get the third position 2. Note, Since we are going to be doing math with these position indices to create the positional encoding for each one, we need them to be floats rather than integers, as I was mentioning, right? So that's the reason we uh, chain it with the float method, uh, float function, and then unsqueeze one. So why is unsqueeze one? Converts the single list. So it's a single list. This gives you a list, but I need it to be a matrix. So I convert it into 3 rows and 1 column. So this is how it should look like once you do unsqueeze. The opposite of this is squeeze. Here is a starting token to determine the y-axis coordinate on the sine and cosine curve. The positional encoding equations used in addition is all you need is this, okay? Sine, so 2i plus 1. So this is the first sequence, the second sequence, so kind of the even odd and even sequences, right? So, and we see that with a sine and cosine function, we divide the position by some number that depends on the index I and total number of PE values we want per token D model. Note, when the index I is 0, then we are calculating the y-axis coordinate on the first pair of sine and cosine curve. Okay, when I equals to 2, then we are calculating the y-axis coordinate on the second pair of sine and cosine curve. So in this example, embedding token equals to torch, arrange starting at 0, ending at D model size, step is 2 and it's converted to float. So why would you set it as step equals to 2? Because notice this is 2 and 2i plus 1, right? So it produces the same result basically. And now finally let's create the div term. So div term 1 by torch tensor and just multiplying that big number with embedding index and D model. Okay. So now we have calculated the positional encoding value. Remember PE was initialized with a matrix of zeros with maximum length. So we are now going to calculate the positional encoding values. And D model, which is the number of embeddings per token column. So 0 to 2 and 1 to 2. That's so this is every other column starting with the first has sine value. Every other column starting with second has cosine value. So it's an alternating value, right? As I showed you. So 1, 2, cosine, sine, cosine, so on. Now we register PE. So self.register buffer. So register underscore buffer ensures that PE will be moved to wherever the model gets moved to. So if the model is moved to a GPU, then even though we do not need to optimize PE, it will also be moved to GPU. And similarly, it can remain in the CPU. Finally, you have a def forward and it returns word embedding plus self.positional encoding. Word embedding size, this is optional, you don't need it. Okay. So now let's discuss about the class encoder. Again, it is built on the init module from PyTorch, and this is the super of init from the init module, taking the parent class init. So what are we passing here? So we are passing the num tokens, D model equals to 2 and maximum length. So num token 4, maximum length 6. So what are we trying to achieve here? We are trying to create an encoder transformer by simply bringing together word embedding, position encoding, self-attention, then residual connection plus normalization and a fully connected layer. So here we have word embedding. So just taking the embedding, um, embedding values from the PyTorch, the embedding module from PyTorch, right? Num embedding equals to num token with the D model as the embedding dimension. That's 2. Then positional encoding, taking that positional encoding class. So D model equals to D model max length. Then we have self attention. So in the attention model, D model equals to D model and layer norm, in layer norm, it's the D model, that's the same dimension that we are passing. So fully connected layer in a linear in features equals to G model, out feature equals to num token. The number of tokens, and so using the fully connected layer. Okay, now we have you have to talk about the forward method. So again, bringing everything together, word embedding. So taking the token IDs, right? Then you use the positional encoding, and then finally you calculate the self attention, right? With the so basically it's the query, so query key and value, right? So query key and value, and with no masking. Then we are so this residual connection values is storing now the value for both positional encoding plus the self attention values, right? So which is not stored in the self attention value. So that's the main reason why you use a residual connection value, then followed by a fully connected layer output that on the residual connection values, which returns residual connection values. So why I repeated two times. So one is the encoder output value and the other is encoder hidden value. So this is important when we are making it or using it in the decoder part, because in the attention you need to send in the in the encoder decoder attention part we are getting the key and the value for the encoder part, and the query generates from the decoder part. So that kind of helps it over here. So in a decoder block that applies embedding, positional encoding, self-attention, add and normalize, and linear projection followed by normalized output. Okay, so let's look at the class decoder. Again, what are the parameters that we are passing? Num tokens equals to 4, d model 2, and max length equals to 6. This remains the same. We are defining the embedding positional encoding. So what is the difference that we going to see in terms of the encoder decoder? So in decoder you'll have a masked attention, right? So self attention was in encoder, you have a masked attention in the decoder part of it. Okay, and then you have a residual connection plus normalization, same encoder decoder attention, which takes the key and value from the encoder and the query from the decoder. So it's kind of the cross attention, residual connection plus normalization, and a fully connected layer. So attention, so now let's kind of define this. So again, in an embedding, so word embedding, positional encoding, self attention equals to attention, and we have to include the mask over here in the forward method. And this is cross attention, initializing the cross attention. Then this is the layer normal norm 1, layer norm 2, and the fully connected layer. So let's look at the interesting part, which is the forward method. So here you have token IDs, encoder K and encoder V. So that comes from the key and value, right? So we need this key and value from the encoder part, right? So these things comes together in our transformer class. So here word embedding equals to self.we word embedding tokens, positional encoding. So these all remains the same. However, here look at the difference. So mask is we are trying to actually initialize a mask. So for decoder only transformer, we need to use masked self-attention, so that when you are training, we cannot cheat and look ahead at what words comes after the current word. To create the mask, we are creating a matrix where the lower triangle is filled with 1 and everything above the diagonals is filled with 0. So the lower triangle 1, everything above the diagonal 0. And that's possible with trill. Okay, so the mask self-attention values is now defined with positional encoding, positional encoding, positional encoding, and the mask. So this computes the self-attention over decoder input, applying a mask to prevent attending to future token. So what was the decoder input? Start awesome, right? So the start token with awesome. And here this one actually or adds the residual connection values is positional encoding plus this masked self-attention value. And then you can pass this to the cross attention or the encoder-decoder attention, right? So as I mentioned, key and value comes from the encoder and the query is from the decoder. So encoder key, encoder value, and the residual. So this is the query, residual connection values, and mask equals to none. Definitely no masking at this cross attention. Then we use the self normalization too, and connect the residual connection values with the X cross attention and fully connected layer results as result to cross attention to see the earlier output and normalize, and finally apply a linear transformation to normalize the outputs. Okay, and then bringing everything together to our final class, which is the class transformer. So again, it has self, num token, d models, max length, super.init, self encoder equals to, we are now taking the initialized values from the encoder. So encoder, then this is from the decoder. So it takes the num token, d model, maximum length, again the same thing. And then we have a final output linear there. So it holds an encoder and decoder with specified token size, model dimension, and maximum sequence length, adds an output linear layer to map final output, and then encode passes source tokens. Right? So encoder passes the source tokens to the encoder to get the encoder output and encoder hidden, and the decoder feeds the target tokens along with the encoder output into the decoder. So returns the decoder output as the model's output. So in the forward, let's look at the forward again. So the encoder is actually returning an encoder output and encoder hidden, right? By taking the source token. And this decoder is inputting this encoder output, encoder hidden along with the target tokens. Okay. So that completes our basic transformer model. So bear in mind it's also a very simple transformer architecture. In general, you will have a multi-head attention, and there are few more modifications that that is actually done in the attention is all you need paper. Okay, so most of the language models are decoder based, but for language translation, transformers with encoder and decoder part is essential, or even for this chat, for example. Okay, I'll just skip this two, and then let's go over to the training pipeline. Those were actually used for generating for model inferencing. So let me talk about the training pipeline first. So hyperparameter. So what are my hyperparameters? Number of tokens. So that is the length of the token ID. Here it's 6. Maximum token length or maximum length is 2. D model equals to 2. Num epochs is 1000. Learning rate is 0.001. Initialize the model. A transformer with number of tokens, D model, and maximum length. Define the loss function and optimizer. Criteria with so we use the cross entropy loss, and here Adam is my optimizer with the learning rate. And then combine everything into a data set. So tensor data set, which is combining it and transforming it to a float and tensor float. And then we create a data loader, so it is useful for iterating. Okay, now we'll talk about the training pipeline. So this is a standard supervised training. Loop for a sequence model, right? So what are we looping through? So of course we are looping through first to the epochs. So epoch loss is 0. We initialize at the beginning of the epoch, and now we are iterating through the data loader, right? So source, target input, target output. Now you might ask me why squeeze 0. So just to make sure that, because I want to keep this as a very simple example, we are not dealing with any patch size. So one common sequence length is actually being used as sequence length. In next lectures, I will start introducing the batch size. For this lecture, just keeping it simple with dimension constraints like with the dimension 1. Right? So that's the reason I'm just squeezing it out. So forward pass output equals to model, source token, source and target input. Right? So giving it the source and the target input, source going into the encoder and target input going into the decoder part, right? And then we are getting the output, flattening it out and also flattening the target output, so target out, and then compute the loss with the criterion, right? And then keep the track of the loss. Now you use the back propagation, right? The backward pass. So loss dot backward and update the weights with optimizer dot step. Okay, so now this moment, let's just look into the generate generate method a little bit. So it's for this simple exercise only. So what it does is implements a step-by-step decoding loop, encodes once, decodes one token at a time using previous prediction as input, and whatever is the top prediction, it picks that. Stops at end or it stops at max token, and it starts with the start token. So it's the start token, it will always start with the start token. Okay, so for I in range, so for loop, so because it has two criteria, either it reaches the end token or either it reaches the max length. So that's the reason we are looping it through the max length, right? So passes the current encoder input to the decoder input to the decoder, gets the last token's output prediction, picks the highest value. So here picks the highest value is the greedy one. So picks the highest probability value, generates sequence, and keep appending the predicted token. So whatever token it has predicted or the top token it has predicted, you just append it to the sequence. So whenever it picks the end, so in this case, awesome end, it has to pick that. So whenever it goes to the end, it will break. Otherwise, if it never reaches the end, it will stop when it generates the max length, right? So update the decoder input, concat the decoder input, mm, comma torch tensor predicted token, and then return the generated sequence. So get the tokens, append the token, append the predicted token to the output sequence. If end token is predicted, stop early, else and keep appending, right? So else, this is the else command over here. Okay, so let's go over and check the results. So if I put this, what is live AI, or live AI is what? And then I'm going over the test input, so it will generate the response. Awesome end for both the results because I've already trained it with the same example, right? So this first pass is provided in the transformer AI weekend project. So it's in under the transformer folder. So transformer chatbot first pass, that's the notebook. And I hope you like this video and subscribe to our channel. Let's learn, build, and grow together. Now we will also follow up with a notebook. So I'll also do a quick notebook walkthrough. And let me just change my screen.